Hello everyone, today we'll be learning parameter efficient fine tuning. So these are the three methods which are currently being used for PEFT, LoRA, QLoRA and DoRA. So firstly, as we learned in previous videos about full fine tuning, so why not to full fine tune? Let's say you are having 7 billion parameters. So to retrain them, it is a very computationally heavy task. It would be requiring around 60 to 80 GB of VRAM. And to get this much RAM, it is not possible on individual GPU systems. So you'll be needing a complete set of GPUs. So it is not feasibly possible for an individual to completely fine tune any LLM. And even at industrial scale, so let's say wherein you will be having these GPU systems of 60 to 80 GB VRAM, the cost and time for training will increase. But there are some benefits also for full fine tuning. So let's say you want to completely reshape a model. Then obviously you will be doing full fine tuning. So it is like building a house after demolishing it. So you can retrain it like the way you want. There's another demerit of doing full fine tuning. It is called catastrophic forgetting. So whenever we retrain or completely retrain anything, then there would be a condition wherein the previously learned data would be just flowing out of your brain. So it happens to us also. Let's say this brain LLM is given a new data which is completely a medical data. So while retraining it, it will be forgetting the things like coding or let's say niche poetry which it used to do earlier. So this will make your model a specialist in medical data but with no common sense. So this is how fine tuning works. You must be knowing about GPT 4.5 Turbo. So it is a base model which is trained on massive amounts of internet data. Over it, we use a full fine tuning layer to get our chat GPT or the generative pre-trained transfer what we have. So, and then again on chat GPT, if you do domain specific fine tuning, basically we use PEFT only for domain specific ones. Because of the demerits of full fine tuning we just learned about. So then after doing PEFT on ChatGPT, you can get domain specific LLMs for finance, for medical things and all. And also ChatGPT could be trained for some tasks too. Let's say you want to build a chatbot for your bank. So you'll be doing PEFT over ChatGPT to get this new chatbot. So this is how fine tuning works. This is our first technique or LoRA, which is low rank adaptation. So you'll be having your base model, which is let's say ChatGPT over here. Then you'll be adding the fine tune weights to it. And then you'll be getting the updated model. But now you'll be wondering that herein we are completely retraining the same thing. So what's the use? So these fine tune weights are not just retrained. They are retrained in a particular fashion. So this complete matrix is decomposed into D cross R into R cross K, where this R is called the rank of matrix. So let's say this 4 cross 4 matrix are divided into rank of 1. So it divides into basically 4 cross 1 into 1 cross 4 matrix. So this is called matrix decomposition. And now what's the use of it? So look over here, this 4 cross 4 matrix has 16 components. Wherein we just downscale it to 8 components over here. These 4 in first matrix and then the other 4. So your 16, so now you don't have to train 16 weights. You will just be training 8 weights. So this is the use of LoRA wherein we are reducing the number of parameters. So this is the mathematics involved behind, like how do we update the weights. So W0 is your base model, W is the updated model. Alpha by R stands for the normalization term. Alpha is just learning rate which we have used in machine learning models and all. R is the rank. As your rank gets higher, so you'll need to normalize it. That's why this term alpha by R comes here. And B cross A is, let's say this is the B matrix and this is the A matrix. So B cross A would give you the fine tune weights. So we are downscaling the parameters here. And the use of rank over here is that as you increase the rank, your parameters would increase, and so will be the precision. So for more precise tasks, you would be needing higher rank, but still, like, let's say the rank is higher, still the number of parameters would be significantly lower than the fine-tuned weights or the base models weights. Like, let's say there are 70 billion over here, so it would be reduced to in millions, obviously. So that's a advantage of using LoRa, because we are training pretty few weights over here now. Then comes quantized LoRa or QLoRA. So what is quantization basically? The parameters which we have in our weight systems are of 16-bit. So to downscale them to 4-bit or 8-bit, we use a technique called quantization. Now, how is this quantization done? So these weights follow a normal distribution or a bell curve. Hence, most of the parameters are around the zero line. So you can't just do standard quantization because it will divide on the basis of equivalued values. Okay, so it would be like, let's say 16 bits, so there will be 16 equidistant lines over here, and the precision will obviously drop. So that's why we use NF4 or 4-bit normal float, which divides this complete space into equiprobable values and not equivalued. After this quantization is done, there's like, before we do the LoRa math or completely this thing of matrix decomposition and then adding it back, so we do dequantization, because now you have downscaled your 16-bit system into 4-bit system, so obviously there will be some precision loss. So in order to nullify it, we use dequantization so that we can convert this 4-bit again into 16-bit. Now you must be wondering, then why did we firstly like downscale it to 4-bit and why not 16-bit itself? So there's a static versus active VRAM trap. So let's say you are having a model of 70 billion parameters. So the static weight of the model, it is itself sitting into your VRAM and taking a lot of space. So let's say you are using LoRa technique or the 16-bit one. So your model would take about 140 GB data, just to your 140 GB space in your VRAM, just to sit there. So if your GPU has, let's say, 80 GB itself, so you will not be able to load it. Forget about training. Whereas in QLoRa, firstly you downscale it to 4-bit. So the model will take up to 35 GB. So you can easily firstly put it into your VRAM and then train individual layers, because obviously you won't be training the complete parameters at once. You will be training it layer wise. So this layer will be dequantized, and then obviously training would be done. The last technique or the newest advancement in parameter efficient fine tuning is DoRA. So it is weight decomposed low rank adaptation. We all have learned about vectors. So vectors can be decomposed into its magnitude and direction. So this concept is used in DoRA. So these weights or the weight vectors are decomposed into its magnitude and direction and then trained individually. So some research over this DoRA paper have showed that magnitude and direction are not correlated. But in LoRa, they are forcefully correlated, because we are not decomposing them, right? We are just using it as it is to add weights and then get our fine-tuned model. So what DoRA does is it will decompose it into magnitude and direction and then obviously train individually. Now, however, this technique leads to a tiny surge in number of parameters as compared to LoRa, because obviously now a single weight consists of two entities, which is magnitude and direction. But then the accuracy will increase significantly because you are training two different entities together, like not together. The two different entities are trained differently and then added over together, so that obviously your accuracy will increase. So DoRA is used for pretty heavy tasks like coding, image generation and all. And also we have QDoRA, just similar to QLoRA, wherein firstly quantization will happen, then vectors will be decomposed, and then LoRa math would be used, and then again dequantization would be happen. So things like that work. And this is the formula for combining these DoRA weights. So this is the magnitude, and then you have the angle parameter. So both of them are multiplied to get the weight thing. So that's all about parameter efficient fine tuning. We'll be looking into the codes of it in the upcoming videos.